Welcome to Advanced Quantum Chemistry and the second lecture on one-electron basis sets. In the previous lectures we discussed that in most quantum chemistry programs nowadays one uses so-called Gaussian basis sets, meaning basis sets made of Gaussian functions. The question now remains how many functions one should use in a calculation and which kind of functions, meaning whether it should be S or P or D functions, and what the exponents should be. Choosing a basis set might therefore appear to be an overwhelming problem, in particular because one would like to choose as small as possible a basis set in order to reduce the computational time, but on the other hand, as large as possible in order to reduce the basis truncation error. Choosing a basis set is therefore a bit of an art. Fortunately, several other people have thought about that and worked on that and developed different kind of basis sets for all the atoms in the periodic table. In the following, I will describe some of these kind of basis sets and come with some recommendation. Now, the starting point is what one calls a minimal basis set, which means one uses only one basis function for every occupied orbital in an atom. For example, for the carbon atom, one would have one contracted Gaussian function representing the 1s orbital, one contracted Gaussian function representing the 2s orbital, and then one set of three contracted Gaussian functions representing the three p orbitals. One should note that one always uses a complete set of p or d or f orbitals, meaning even though in carbon only two of the p orbitals are occupied, one always, if one uses a basis set for carbon, one would have three p functions. Or if one wants to have some d functions, then one would use either 5 spherical or 6 Cartesian d functions, and correspondingly 7 spherical f functions or 10 spherical f functions. Now, such a minimal basis set is not very accurate. Actually, it's rather inaccurate. So it can only be used to give qualitatively results. If one wants to have some better results, then one would use what is called a double zeta basis set. And a double zeta basis set means that one uses two typically contracted Gaussian functions for each atomic orbital. And those two have different exponents. So for example, the 1s orbital, again of carbon, one would have two different Gaussian functions with two different exponents. And again, for the 2s, one would have two with two different exponents, and so forth. Even better would be to use a triple zeta basis set, where one then would use three Gaussian functions with different exponents for each occupied atomic orbital in an atom. And one can continue that with quadruple zeta, pentuple zeta, and so forth. Now, what one found out there is that this is very good and very important and necessary for the valence orbitals, for example for carbon, the 2s and 2p orbitals, but it's actually not really necessary in most applications for the 1s orbitals, because the 1s orbitals might contribute a lot to the energy of a molecule, but this contribution does not change very much going from one molecule having a carbon atom to another molecule in a carbon atom. So having a carbon atom. So if you're interested, for example, in calculating reaction energies, this contribution of the core, the inner electrons, does not really change, and therefore it's not so important to describe this very accurately. So this led to the idea of what is called a split valence basis set. And that means that for the core orbitals, carbon would be 1s, carbon, nitrogen, oxygen, fluorine would be 1s. For silicon, for example, that would be 1s, 2s, and 2p. One only uses one contracted Gaussian function for each core orbital. Typically, these contracted Gaussian functions for the core orbital actually consist of maybe 6 primitive Gaussian functions contracted to 1. And then for the valence orbitals, 2s, 2p for carbon, 3s, 3p for silicon and so forth, one uses then a double zeta or triple zeta basis set. And nowadays there exist basis sets which go up to even hextuple zeta or heptuple zeta, meaning 6 or 7 Gaussian functions with different exponents for each of the occupied valence orbitals. The acronyms for these so-called split valence basis sets are VDZ, valence double zeta, or VTZ, valence triple zeta, and so forth. So far, so good. However, one quickly found out that if one wants to describe the formation of bonds accurately, then it is necessary to add also some extra functions. An extra function means functions with a larger angular momentum than the occupied atomic orbitals would have. And these functions are called polarization functions because they allow then to introduce some polarization of the occupied orbitals. Let's take the very simplest example. Let's take the hydrogen molecule, for example. Here, let's take 2 hydrogen atoms, and any of the basis sets we had so far, be it a minimal basis set or valence double zeta or valence triple zeta basis set, for hydrogen would only include s orbitals. So we would have different s orbitals located at the 2 hydrogen atoms. And these s orbitals on the 2 hydrogen atoms, they have a spherical symmetry, also in the hydrogen molecule. But of course the hydrogen molecule does not have the spherical symmetry any longer. And in particular, we want to describe the region between the 2 hydrogen atoms very good, because that's where there will be some more electrons forming the bond. And how can we do that? Well, the way to do that is, of course, if we allow the hydrogen atoms also to have, for example, p orbitals, because at least 2 of the p orbitals are then directly orientated along the internuclear separation, along in the region where the bond is. So for hydrogen, p-type orbitals are polarization functions, and they are important to include if one wants to describe bonds between the atoms. Correspondingly, for carbon, one would then include d-type basis functions for carbon, nitrogen, oxygen, and for atoms which have occupied d-type orbitals, one would include f-type basis functions. Now, if one wants the more accurate calculation one wants to have, the more polarization functions with high angular momentum one would actually include in the calculations. It's not only, and these polarization functions are important for describing bonding, but they're not only important for describing the bonding situation, but also many other molecular properties, like, for example, UV spectra. It's important to have included polarization functions in the basis set. Another type of functions which one often wants to include are so-called diffuse functions. And under diffuse functions we understand Gaussian type functions which have much smaller exponents than the normal valence orbitals have. And they're important for the description of electric properties. For example, if you want to calculate the dipole moment or polarizability of a molecule, as we will discuss later in the course, it's important to include diffuse functions. It's also important to include diffuse functions if you want to describe, for example, anions, because there the electron density will fill a much wider part of the space than for a neutral molecule. So diffuse functions are functions with small exponents. That can be S and P for carbon, but sometimes it's also important then to include diffuse polarization functions. On the last slide, I want to mention now some of the most used series or families of basis set. The oldest of the 3 families of basis sets, which I want to mention here, are the so-called Popey basis sets, because they were developed in the group of John Popey many years ago, and they are the ones which in a way are the standard basis sets of the Gaussian program. Remember that John Popey got, I don't know, 20 years ago, the Nobel Prize for his contributions to quantum chemistry, and one of his big contributions was starting up the Gaussian program and developing these kind of basis sets. They have a quite particular notation, which looks like this, where before the dash here, that's the number of primitive Gaussian functions which are used for describing the core orbitals. So all these Popey basis sets are actually split valence basis sets. So you use one contracted Gaussian function for the core orbitals, and here in this 631G series, you use 6 primitive Gaussian functions for one contracted Gaussian function for the core orbitals. And then after the dash, you have a description of what kind of Gaussian functions you use for the valence orbitals. And the number of numbers tells you whether it's a double zeta or a triple zeta. So here you have 2 numbers, so this is a valence double zeta. Here you have 3 numbers, so this is a valence triple zeta. And then again, like for the core orbitals, the number which stands there actually tells you how many primitive Gaussian functions are included in the contracted Gaussian functions. So a 631G basis set has one contracted Gaussian function for the core orbitals consisting of 6 primitive. It has two contracted Gaussian functions for each valent orbitals, where there is one of those consists of 3 primitives, and the second one is just one single primitive Gaussian function. And this single one has a smaller exponent than those 3 here ones. So a 6-31G base set is a valence double zeta base set, whereas a 6311G basis set is a valence triple zeta basis set. And then there's some notation for the polarization functions. So a star means, the first star means polarization functions on all the atoms which are not hydrogen. And if you have a double star, the second star means you also have polarization functions, which means p functions then on the hydrogens. There's actually also another nomenclature which I haven't mentioned here. If you want to have diffuse function, then for example a diffuse function would be notified with a plus. So this would be a valence double zeta with a set of diffuse S and P functions. So one S and one set of P functions with rather small exponent for the non-hydrogen atoms, and again with double plus it would be also for the hydrogen atoms. The second family of base sets, which is very often used, is the so-called correlation consistent basis sets developed by Tom Dunning. So it's Dunning's basis set, and they are always include polarization functions. And this correlation consistent means that the exponents and the form, how the basis sets are built, was sort of optimized in not hard-to-fork calculations, as actually the Popey's basis set originally were developed for, but in calculations which include electron correlation, as we will discuss later on. There's a whole series of that. There are double, triple, quadruple, and for some of the atoms it actually goes up to 7. What is particular for those Dunning's correlation consistent basis set is, as I said, there are polarization functions always included, and which polarization functions are included changes depending on the double, triple, and quadruple zeta. So for the double zeta, the polarization functions would be D functions for carbon and P functions for hydrogen, whereas in the triple zeta, you would, for carbon, nitrogen, oxygen, you would get 2D functions and 1 F function, whereas for hydrogens you would get 2 P function and 1 D function. And for quadruple zeta, it goes even further. So the higher you go up in the with respect to how many functions you use for describing the valence function, you also get, in each step, you get one polarization function with one higher angular momentum also included. Also here you can get a version of these basis sets which include diffuse functions, and they are called augmented and approximated in this way, augcc pvx set. And again, like with the polarization functions, the augmentation functions you get in the double zeta, you would get for carbon, nitrogen, you would get a diffuse S, P, and D function, because you also get the diffuse polarization function. And for in the triple zeta, for carbon, it would be S, P, D, and F. Whereas in Popey basis set, those diffuse functions are always only S and P functions. So only the occupied valence orbitals, you get a diffuse function. As a consequence of that, that you get many more polarization functions, and also that the diffuse functions you get of all types, these Dunning correlation consistent basis sets are much larger than Popey's basis set. Recently, some years ago, maybe 10 years ago, there was developed by Frank Jensen and Aarhus another series of basis sets, which is actually optimized for density function theory calculations. So they are made for DFT. They are made in a similar way as Dunning's correlation consistent basis set, but whereas these are made for couple cluster and configuration interaction calculations, Jensen's basis set are made, as I said, for density functional theory calculations and Hartree-Fock calculations. But they are in a way similar build, which means that with ever increasing, when you go from double zeta, triple zeta, quadruple zeta, you will also get more and more polarization functions of increasing higher angular momentum. And in both series of base sets, they are built in the way that the change in the energies which you get from going, for example, from double zeta to triple zeta, and the change in the energy which you get by adding polarization functions are of the same order of magnitude. So both are very well balanced series of basis sets. Frank, for some reason or other, chose a different notation. So he called them polarization consistent. That's a bit the same like the correlation consistent. But he didn't use this double, triple, quadruple zeta kind of nomenclature. He just gave numbers, whereas the n equals to 1, that is just a normal double zeta basis set without polarization functions. N equals to 1 is then a double zeta with polarization functions, and n equals to 2 is then a triple zeta with polarization functions. So the numbering of n here is sort of 1 lagging behind here. So a double zeta, polarized double zeta is n equals to 1, a triple zeta is n equals to 2, quadruple zeta would be n equals to 3. Good. All these three series of base set, Popey's, Dunning's, Jensen's, they are all made and optimized for the calculation of ground state energies. And they work very well for those. But we're often also interested in a lot of different other properties like excitation energies, or for example like NMR coupling constants or ESR spin-spin coupling constants. And for these kind of calculation, these energy optimized basis sets are not particularly good. So some people, including myself, started to make modifications of these basis sets so that they perform better for particular types of calculations. So we have developed modifications of Dunning's basis set, which are made for NMR and EPR calculation of coupling constants, and we call them AUXCCPV-J for NMR spin-spin coupling constant, and sometime later we also made a similar modification of Popey's basis set, including J. In the meantime, Frank Jensen also has taken up the same idea and made some modifications of his basis sets, which are then called PCJN. And actually, he also made similar modification of his base set for the calculation of NMR shielding constants, which are called PCSN. Many of these basis sets are included in modern quantum chemical programs, but But if you can't find any of those spaces in the program you're using, you could also have a look at this web page where you find a periodic table and from which you can download many of these space sets.